Okay, well, good afternoon, everybody, and welcome back to the Scottish Contaminated Land Forum Conference 2021. My name's Thomas Aspray. I'm a technical manager for ERS, and I'm going to be chairing this third session this afternoon. So this conference wouldn't happen on this platform without the support of our sponsors. You can see today's sponsors here on the slide. So we've got Juta, Clyde Ground Investigation, ERS, I2 Analytical, and VHE. And for those that were on yesterday's conference webinar, we had videos at the end of the session from each of our sponsors. So what I'll do is ask that at the end of this session that you just show your appreciation to those sponsors for supporting the event and just watch a short 10-minute video at the end there. So we're also on social media for the conference. So you'll see the Twitter for SCLF, or the Scottish Contaminated Land Forum, there at the bottom, using the hashtag as well, SCLF 2021. So there'll be some posts going out, or have been already. It'd be great if you can like them, share them, engage with some of the questions that will be there as well. If you're not already a follower on LinkedIn as well, you can see SCLF on LinkedIn, so please ask you to join that. So housekeeping, very easy when you do a conference online, I think. So basically you've come in with your video and your microphone off. But what would be great is if people really engage with the question box. So anytime, any technical issues, fire them into the question box, and the back team made up of the SCLF committee members will help you with whatever problem you're facing. Otherwise, any questions for specific speakers or in general, or points that you want to raise, then this is your place to do that, and it'd be great to get engagement through that question box as well. So we are on to the third session. You'll see the title of the session there is on innovative low carbon sustainable remediation approaches. So I get the most long-winded title, I think, in terms of sessions. We've got three really interesting talks. I think we'll see some data today, which will be great. I'm always interested in seeing that. So I'll introduce each of the speakers when we come to them in turn. Very excited to hear about the GeoEnergy Observatory. Certainly been some discussion about that in our office, so hearing from Alison about that. And then Keith talking about the circular economy, which obviously we touched on in a few talks yesterday in terms of dredged sediments, and then looking at passive mine water treatment in Wales. And I think that's interesting from hearing, I think, about some pilot and trial data from that project. So we'll go through the three presentations, and then same as last time, we'll have a panel Q&A. So yeah, make sure that you get your questions in throughout those presentations, and that will give us plenty to discuss with those three speakers. And then, as mentioned, we'll have that meet the supporters at the end. Before we get on to the first presentation, we'll just use a few minutes to have a look at some questions, trying to build on some of the discussion from yesterday. So the first poll question that we've got, Eve, if you want to fire that up, what would be most effective in our industry to help meet net zero? And you should see a couple of options there. So we'll just give 30 or so minutes, seconds, sorry, not minutes, for people to just answer that question. Let's see what people think. So I can see a comment already in the questions. Well, it's both. Again, so yeah, that's grand. Eve, do you want to close that poll and just let me know how that went?
Hi, Tom. So 57% carrot and 43% stick.
Okay, so a little bit more carrot than stick in our audience for that one. Great. Well, we've got time, I think, to launch the other poll as well. So we've got another poll to go, which slightly different question. How important is industry collaboration to meeting net zero? So again, if we could just launch that poll. Let's see what people think about that one. Well, that's very clear cut. Eve, I can see the responses actually myself. So yeah, we've got 94% saying vital, 6% saying helpful, and obviously then 0% saying not important. So yeah, pretty clear cut that one, and that's an interesting one. So great conferences like this, obviously we're in a slightly different format, but important opportunity for people to hear, come together, and then go away and collaborate afterwards. So I think what we'll do is we'll get ready for our first speaker. If you want to join Alison, and we'll make Alison the presenter. And okay, so yeah, our first speaker is Alison Monaghan from British Geological Survey, and she's the principal geologist based in Edinburgh. Is that at the Lyle Centre, Alison? Are you based at Lyle? Right. Okay, great. So on the Heriot-Watt University campus, and she's leading the UK GEOENERGY Observatory in Glasgow, so an underground laboratory, as it's described, focusing on shallow mine water, geothermal and heat storage, environmental change and impact. And Alison's background is in carnivorous geology and geoenergy onshore Scotland and offshore in the UK. So Alison, I'll hand over to you, and yeah, look forward to your presentation.
Okay, thank you very much for having me today. So yes, as was stated, I'd like to talk about an underground laboratory today. So that's, I guess, repurposing and reusing an underground resource. I'll just get my slide to move. All right. Okay, right. So I think we're all aware the importance of meeting net zero carbon emissions targets, and one of the biggest challenges we have for our energy systems is decarbonising heat. This is going to require a major policy shift in our energy system, and those changes are coming through. So on this slide, you can see some of the reports, the government reports and International Energy Agency reports, looking at ways we can decarbonise energy, and all of these contain information about decarbonising heat. So, for example, if we look at the UK government energy white paper, which came out at the end of 2020, then there's a range of technologies for decarbonising heat and heating our buildings, from heat pumps, that's both air heat pumps and ground source heat pumps, biomethane, hydrogen, district heating networks, and geothermal energy. And it's that latter one I'm going to talk about today, using the underground. And in a more of a Scottish context, similarly, the Scottish Government obviously has an energy strategy, a climate change plan. It's done a lot of work around decarbonising heat, current legislation around district heating networks, and so on. The Scottish Government also has its National Performance Framework, which has an environmental aspect to it, which obviously covers energy, and energy from renewable sources is one of the aspects of that. And those link to the Sustainable Development Goals. So there's a lot of kind of policy and strategy around this area, but it is a really big challenge. So on the right-hand side of this slide is a graphic from the Scottish Renewables website with data from the Energy Saving Trust. And we can see that in Scotland, this was in 2019, the renewable heat was about nearly 5 gigawatt hours of heat, but the heat demand in Scotland is around 80,000 gigawatt hours. So only about 6% of heat in Scotland is currently renewable. So that's a big change that needs to happen. Whilst we've seen big changes in electricity, heat is more challenging. So we need to use all the different tools that we can to decarbonise heat. And so today I'm going to talk a little bit more about one of those types. And actually it's something that has been in Scotland for quite a long time. So on the right hand side of this slide are two images of housing schemes in Glasgow and in Fife. And these are actually two schemes that were heated by mine water energy from, well, one from 1999, one from 2001. So this is using the heat from old mine workings through heat pumps to heat homes. There are other schemes in England, but it's something that's not taken off widely, but it is a great use of our legacy mining infrastructure. The pictures on the left-hand side illustrate mining under the ground in the case of this top picture, and the bottom picture illustrates some mine workings. These are bits of coal. They're mine workings that have been exposed in an open cast site, but they're a type of mine working we call stoop and ream. And really, if you can imagine, you hadn't taken the layers of rock off in the open cast site, and these were buried underground and they were flooded, then you have a lot of water in the old mine workings. And it's that water in the old mine workings that we can use, we can pump out and extract the heat. And I'll show a diagram on the technology in a little minute, but really to just understand where that heat is residing in the underground. And that Scotland actually has been a world leader in some of these schemes for some considerable time. Unfortunately, both of these schemes are not operating currently. So just looking more broadly across central Scotland, I'm sure many of you are aware the extent of legacy coal mining across central Scotland. So on this image, the purple is the extent of coal mining across central Scotland. So all the way across the central belt, we have numerous coal fields. And the sort of grey colour is the urban areas. And what's noticeable is that these areas of mining and urban areas are coincident, not surprisingly, because a lot of them grew up around the coal mines. So for the purposes of heat, that's very good, because heat is more difficult to transport than electricity. So having the heat where you need it is a really good thing. So the coincidence of urban centres and old coal mines is really helpful. It's also a very large resource. There's an awful lot of coal mining underneath central Scotland. I've not put a number here. People have come up with numbers for the size of the resource, but really it depends on how sustainable you want the resource to be. And one of the things I'll talk about in the next slide is we can take heat out from underneath the ground. We can also potentially store heat under the ground interseasonally. And so it's not as simple as just saying we can take this much heat out. It's about having a sustainable, renewable system. So as I mentioned, there are schemes in Scotland, but there are barriers to the widespread rollout of technologies such as this. So there's technical risk, and that's mainly what I'll talk about today in the talk about the observatory. The economic case can be challenging. There's a lot of upfront costs, and then there are operational costs compared to other technologies. And there's still quite a lot to be refined in the regulation and policy arena in terms of heat ownership and so on. The Coal Authority manages the mine working legacy, as I'm sure most of you know, and has many schemes in planning across central Scotland. So they're really the people that on the ground implement a lot of these schemes or are involved in the implementation. So moving on, I'm just going to give a quick summary of how mine water heat works. So this slide is helps me to explain. So this is a cross section of our underground from the surface down to 100 meters. Our water table is up here, so it's high, and we've got lots of old mine workings within the bedrock. So mine water geothermal works by abstracting warm water. It's not hot, it's often just between 12 and 20 degrees, but extracting warm water from a borehole, pumping it to the surface, and then taking it through a heat center and a heat pump where the heat is exchanged and pumped. Often heat is supplied to homes and businesses on a separate loop, so it's not mine water going into people's homes. And then the relatively cooler water is put back into the mine system at a different place, some distance from the existing borehole, so it's got time to warm up again. And so it's a renewable system. It's not, you are pumping quite a large flow rate, and that's why the mines are important, because they give you that flow rate, but you're not changing the water level significantly in these systems. You're taking out and you're putting back in. And the heat pumps have a coefficient of performance of around 4, so you tend to get out about 4 times as much energy as you put in terms of electricity to run the heat pump. And it's a sustainable system because the heat in the earth is renewed both from solar heat and from geothermal deep heat from the earth's core. So in order to address some of the challenges around this, some of the technical risks, and improve some of the policy and regulation and the evidence base around this, the UK government has invested £9 million roughly in this underground observatory in Glasgow. So I'm sure most of you know where Glasgow is. But this is in more detail where the observatory is in Glasgow. So this is us looking west roughly. This is the city centre of Glasgow over here. And we're in the eastern side of Glasgow in the Clyde Gateway urban regeneration area. And many of the boreholes that form the infrastructure for the underground observatory that go down into the coal mines are situated on the Cunningar Loop, which is situated in this large meander of the River Clyde. So this is Darmarnock over here, and this is South Lanarkshire and Rutherglen. And the boreholes are located in this place because underneath the ground there are up to 7 mined coal seams. They originated from a colliery that was just in the vicinity of underneath this box. The boreholes are of different types. We have mine water boreholes that target the mine workings, and I'll show some more images in a moment. We have in purple, the purple dots are environmental baseline monitoring boreholes. So those are shallower boreholes that go into the superficial deposits or the bedrock above the mine workings to monitor the ongoing change. And then we have one borehole as part of the observatory, which is right over in Darmarnock, this is the deepest borehole. It's 199 meters deep, and it's a seismic monitoring borehole now, but we had a cored geological section from that borehole. The boreholes at Cunningar Loop are of varying depths from 16 meters to about 85 to 90 meters deep. So they're not hugely deep boreholes, but they encounter the coal seams. This area of the Cunningar Loop, it is an area where there's quite a rich history of land use. So there's an old waterworks buried under the northern part of the Cunningar Loop. There's demolition rubble from demolition of the Gorbals over much of the Cunningar Loop, and some kind of municipal waste. And closer to the colliery, there's some old coal mining tip waste. So the shallow subsurface in this area is quite complex, and in order for it to become a public park, which is what this part of the loop is, there was a lot of remediation work done in public areas of that park. So it's a fairly typical area of many of the towns and cities across the UK in terms of its industrial legacy, and that's intentional. That is challenging some of the aspects we've had to deal with, but that's really what it's like in the urban area. So just describing a little bit more what the Glasgow Observatory is about. Excuse me. So as I've mentioned, we've got boreholes, we've got 12 boreholes, and then we've got 4 fenced research compounds. So you can see in this picture, we have a lot of instrumentation in the boreholes so that we can measure flow, temperatures, conductivity, levels, and so on. Obviously, the boreholes are there for people to come and do sampling and to do monitoring. There's been a programme of public engagement which is ongoing around the observatory. Possibly of interest today, and I've got some slides on this later on, is there's a lot of work being done on the environmental baseline before we started work drilling the observatory and before researchers come and use it. So I'll talk about that in a little while. And one of the key things about the observatory is that the data is open. So we've already got a lot of open information on the website, which is summarised here. So that's really important from a public approval point of view to have that data openly available, and it's also there for specialists to use, obviously. So moving on, just to give you an understanding of what the boreholes are like, this is a slide looking at the coal mine boreholes. So this is 4 boreholes summarised in these diagrams, and these diagrams are from about 40 to 90 metres deep. But just to show you really that the boreholes penetrate, well, they penetrate through 3 levels of coal seams: the Glasgow Upper Mine Working, the Glasgow L Working, and the Glasgow Main Mine Working. And the boreholes have got fibre optic cables down the outside for direct temperature sensing down the outside, and also electrical resistivity tomography cables to do cross borehole flow monitoring. They also have hydrogeological data loggers within them, and the boreholes are just screened at the section of interest. So they're screened at, these boreholes are just screened at the mine workings, and the mine workings encountered. The upper is a mixture of wastes and stoop and room workings, and the Glasgow Main, which is the other interval that's screened across, are open voids and waste, mining waste. So this diagram just shows a sort of 3D view of that, just to give you an impression of 9 of the boreholes that penetrate these different coal seams. So this is our deeper coal seam that 3 of the boreholes were drilled into, and the Glasgow Upper coal seam that another 3 boreholes were drilled into. And the idea with these is they're in a triangle so that people can study the spatial variability and also the depth variability. And what we're doing just at the moment is a detailed design and implementation for geothermal infrastructure to be installed within the boreholes, and for a small heat centre to be installed on site. We don't have a heat user because it's a research infrastructure, and that gives us flexibility. But that infrastructure should be there in place by early 2022. And what that means is there's a range of research and development themes that we hope people will come and use the observatory to look at mine water energy. So looking at the resource side, the environmental management, looking at the development of sensors and technologies to reduce cost and risk, looking at changes in the subsurface. So what happens when we use the geothermal infrastructure? What sort of responses do we get in the underground? And also as a place where people can come and do training and engagement to improve people's understanding of these kind of technologies, and improve the supply chain and training of those people who hopefully in the future will be installing these kind of systems. So for this audience, I thought I'd maybe mention just a few of the environmental considerations during the construction of the boreholes that might be something you're interested in. So as I summarised before, the made ground in the Cunningar Loop has really quite a complicated history of mining and waterworks and demolition infill. So it's around 8 to 10 metres thick, often the made ground in this area. And this is a borehole log description, so it's got all sorts of brickwork, cement work, roots, timber, clinker, slate, plastic and glass, and so on. So when we designed the boreholes, we very much looked at the environmental impact side. So the boreholes all have 3 casing strings, so that, for example, the made ground is sealed off from the superficial deposits, and the superficial deposits are sealed off from the bedrock. We looked at things like sealing the individual mine workings as we drilled through them so that we didn't mix groundwater from the different mine workings until we knew that actually the groundwater chemistry is fairly similar across them all. And we also had challenges thinking about how to dispose of the mine water when we were sort of testing the boreholes. And actually we were able to dispose of water in the River Clyde because of the water composition after a little bit of passing through settling tanks. So that was good, but it was a real challenge to know what to do with that water until we knew the chemistry of it. So again, I thought today I'd just cover the environmental baseline really briefly. Really, all this data is available, it's openly available. So it's just to give you a flavour, and yeah, it's there, and it's something you can look at in more detail. But just to give you an idea, we did soil chemistry surveys before we started drilling. There's gas surveys, ground gas surveys, surface water chemistry data sets, groundwater data sets, ground motion, and the seismic monitoring. So just 3 slides really quickly, just to show some of that data. So this is an example of the soil chemistry data set. This is a plot of lead, and also there are box and whisker plots and the data set. This is chromium-6, which obviously was a species of interest in this particular area, which actually was quite low in this area. These are examples of the types of surface water. So at the moment, there's 14 months of surface water data that we've put out from different surface water sampling sites. So there's all sorts of information in that data about, this is a specific electrical conductivity plot. These are samples from the River Clyde. This is from a tributary, which is much more mineralised. This is the plot of iron over the year in the Clyde and in the tributary, for example. And we also did the gas surveys, and we hope to carry on doing those. The summary of the gas survey so far is that we can't see any evidence of mine gas. So I'll just skip this slide. So I'm just going to finish off just to say we'd really like people to come and use the observatory. It's there for people to use. The details are on the website. And it's the kind of thing you can use for whatever your particular area of research is. My final slide is just stepping back again, just to look at mine water heat and the potential for decarbonised heat across Scotland using mine water. There are significant opportunities in the former industrial areas across Scotland's central belt for mine water heat, and also for thermal storage, which is not something I've really covered today. So we're really lucky in Scotland. We've got a kind of unique world mine water research innovation infrastructure where people can come and do their own research to increase the evidence base about how to transfer heat sustainably. You can come and study looking at monitoring and managing any wider impacts of those technologies or subsurface change, and innovate technologies all towards the decarbonisation of heat or underground energy storage. Thank you.
Thanks very much, Alison. Really interesting presentation there. So just while we're changing over presenters, just take the opportunity to fire any questions that you might want to ask, or you might want me to ask of Alison in our QA session. Eve, if you want to just bring up Keith now as a presenter, we'll move on. Okay, so second speaker is Keith Torrance, and I think many of you will know Keith, based at Strathclyde University. He's going to be talking to us about can dredged sediments kickstart the circular economy? So an interesting question title there. Keith is a certified professional geologist, as I said, based at Strathclyde University, but worked elsewhere, including in Alaska. And returned to Scotland in 2019 to take up a position working with Richard Lord at the university and focusing on this topic in terms of beneficial reuse of dredged canal sediments. So I'll hand over to you, Keith, for your presentation.
Can you hear me now? Yeah, well, thanks, Tom, and thanks for the opportunity to speak today. The title of my talk is Can Dredged Sediments Kickstart the Circular Economy? I hope to show that the route to reducing waste and developing a truly circular economy begins by looking at some of the rudimentary operations such as dredging waste. I want to acknowledge the contributions of our partners, including Scottish Canals, Mackenzie Construction and Royal Smiles. This work was funded by the EU via Interreg through the SURICATES programme. So I've previously presented to the Scottish Contaminated Land Forum on dredging, so I don't plan to recover most of that ground. I do want to talk about the SURICATES project and also some of the regulatory aspects of dredging. But for most of the talk, I plan to focus on our largest pilot study to date, which was at Laggan on the Caledonian Canal, and detail the effort that we made to recover usable construction materials from this pilot. So dredging is happening around us all the time. I took this photo last year of the HAM 316 dredger working on the River Clyde, which was there for, I believe, about 6 weeks in total. Within the EU, there is a large volume of sediment that's dredged, roughly about 200 million cubic meters, which, as was said, is classed as a waste. So only about 2 million cubic meters of that is reused. So there are great opportunities for more reuse and to contribute to the circular economy. The University of Strathclyde, it's a partner in the SURICATES project with Scottish Canals, and to date we've run 3 pilot studies on Scottish Canals. Great, so dredging is required in every navigable waterway, including the River Clyde. This was a photo taken a decade or so ago. It shows the practice of putting dredging sediment into some of the old docks along the River Clyde to infill that for future development. This practice is no longer allowed, and the normal disposal method at the moment is to dump that sediment at sea. However, there is a kind of growing realization that we need a more sustainable practice and reuse this sediment for beneficial use. So you're probably familiar with the central diagram showing the circular economy. I've superimposed that on top of a drawing of the Falkirk whale, which I think is a nice analogy for beneficial reuse in the circular economy for dredged sediments, where we're taking the sediments and ultimately reusing it for some beneficial use such as flood control. Some treatment of the sediment is going to be required before it can be reused, and I will talk about that via our pilot study case study. So just a slide on the SURICATES project, which is funded by EU's Interreg. We have currently 12 partners, actually, I'm sorry, 13 partners, including 2 partners that have come on board for the final stage of this project. It's going to run until 2023, and each of the partners is responsible for delivering various different parts of the project, and our part are to conduct these pilot studies. We work closely with Scottish Canals, who have a statutory obligation to maintain the navigability of the canal network, and therefore have a strong interest in reducing the volume of dredged material that has to be disposed of to landfill. Great, of course, it's not quite as straightforward as that. There are many barriers to sediment reuse. As it comes out of the canal, you can see in this photo it's not particularly appealing for reuse. And there could be issues such as contamination, especially in the urban canal network in Glasgow and parts of the Union Canal. We also have to contend with the high water content. It's typically about 80% as dredged, and also generally some high organic carbon content, which precludes the sediment being used for say concrete, because it impacts the final strength of the concrete. So some dewatering is always going to be required, and other forms of treatment may or may not be required. And then finally, the particle size distribution of the sediment, it must be compatible with the final reuse. Okay, so I wanted to put this slide up just to kind of give you an idea of the complexity of the regulatory framework for dredgings. Because they are waste, the Waste Management Licensing Scotland regulations of 2011 come into play. Disposal to landfall is the default option for freshwater sediment, although disposal at sea is still an option for marine dredgings, which actually includes most of the River Clyde, which is of course a tidal river up to Glasgow Green. Those are authorised by Marine Scotland. Within the land disposable waste management licensing regulations, there are a number of exemptions that can be applied to dredgings, provided certain conditions are met. And you know, for this audience, perhaps the paragraph 9 exemption, which applies to brownfield sites, is most of interest. And often brownfield sites are, you know, conveniently situated next to waterways, especially if you think of the River Clyde. So that does open up some possibilities for reusing dredgings on brownfield sites. Great. Well, today I really want to talk about our most recent pilot study, which was conducted at Laggan on the Caledonian Canal. This photo is taken looking kind of south down the Great Glen towards Fort William. You can see Loch Lochy in the kind of immediate background there. And looking in the other direction, you would ultimately end up at Inverness. You can see really how steep the sides are of the Great Glen in this photo. And that's important because the reason we are dredging at this location is because there's a high input of sediment into the canal from one of the many burns that actually feed into the canal. This is the Laggan burn, and you can see successive storm events have built up quite a large deltaic structure in the canal that is an obstacle to navigation on the canal and has to be removed. So as part of this, pilot, we dredged approximately 11,000 cubic meters of sediment from the canal, which were placed into specially designed and constructed cells with a view to doing some gravity separation of the material into fractions that could then be reused. So if I show you this photo, you can actually just see the top of the sediment fan at this location. The canal should be about 4.5 meters deep at this point, but you can see it's kind of peeking over the surface there. You can probably also tell that it's quite a fairly coarse but clean sediment there, unlike the material in the previous slide. And that really reflects the rural environment or location of this site, and also the geology of the surrounding area. So we do know that this material, it tends to only go into the canal during large flood events, heavy rainfall, which unfortunately are becoming more and more frequent as our climate changes. So that has a lot of impact on the maintenance of the canal. So this is kind of an ongoing problem that will have to be addressed, every decade or so. Just a light location here, you can see actually the main A82 road running alongside the canal, and also the location of the two cells that were planned for this project. So a major consideration really was transporting sediment from the canal to the site. The actual dredging site is not really accessible by any vehicles, so we decided that it was important to use suction dredging so that we could actually transport the sediment via a pipeline to the site, and that would pass underneath the main road and avoid any additional traffic and disruption to the A82, which is a major road there. So this photo is taken above the canal, looking towards the two cells there. You can see them in operation. There's an upper cell that's kind of partly hidden by the trees at the back, and the main kind of lower cell is in the foreground here. You can also see a bus in the A82 going by. Okay, so starting with the dredging, this is the dredging vessel that Royal Smiles provided. You can see the pipeline coming out from that. The actual dredging is done by a kind of cutting head, which disrupts the sediment, and a powerful motor will suck water and sediment along the pipeline and then directly to the disposal site. The pipeline's connected into a kind of standard industry screener to remove the larger class and separate actually 3 coarse fragments. Some of the material you can see in the left there. So it turned out actually a large percentage of the gravel fraction was organic, being mostly kind of pine cones coming into the canal. And we were able to separate out quite a large percentage of the organic matter, in the screener very simply. So from the screener, the material was poured into these cells, and the buns within the design of the cells, these buns directed the flow through the cell, as you can see with these yellow articles. And really the idea being that the heavier, larger particles would drop out of suspension in the upper part of the cell and get progressively finer. So one unexpected consequence we had was that the water that was kind of flowing through this cell constantly reworked the sediment and removed a lot of the organic material, so that the sediment was became progressively finer, cleaner. We also saw that some of the wind action, it was actually fairly dry and windy when we did this trial, and that was a further way that the organic matter was removed from the sediment. And you can actually see in this photo, this is at the top, just how clean the sand fraction is as it comes out of the discharge chute there. In the lower scale cell, which was connected via a pipeline, again it flows through these buns and ultimately would discharge back into the canal via another pipeline. The dredger pump, operated typically about 12 hours each day, so that over the night time settling could occur. And we had some instrumentation in the cells. We used the transducer to record some of the water levels that you can see in this chart here, and you can see the kind of daily rise and fall of the water level when pumping was going on in this slide. One interesting thing, of course, is that the drawdown was fairly rapid, and I think that reflects the the kind of porous nature of the gravelly soil underneath the cells. So they drained actually pretty well. But you can see as more fine material was deposited in the cells, the drawdown became progressively poorer and poorer there. Okay, so the goal of doing this really was to try and recover some workable, usable fractions from this material. And you can see in this slide that we've roughly got some coarse sand grading into fine sand, and ultimately silt and clay in that bottom lagoon. Just to put some numbers on that, you can see we're almost 95% sand fraction in the upper lagoon, and dropping down to maybe 50% silt towards the bottom part of the lower cell. So quite a good separation there, and really all of the material in the upper cell was a usable sand fraction. You can also see too that the organic matter drops from under 1% in the upper lagoon to maybe as high as 14% in the bottom cell, again showing that the finer material has accumulated with the silt fraction. Okay, so by the close of dredging, we produced a number of different sediment fractions. From the screener, we got smaller fractions of some fairly large cobbles. If you look at the dark pile behind this, you can see how much of the organic matter is composed of the gravel fraction there, and that's kind of mostly pine cones, which are kind of the same size as that gravel. So the screener was very effective at doing that. And this pile had kind of had the consistency of bark mulch, and has some uses in its own right there. Okay, so this table really just shows what we recovered from the upper cell, including those from the screener there. And we had almost 6,000 cubic meters of sand fraction in this cell that there is a usable material. And the final column there, I've put some of the proposed reuses. This sand fraction we hope to be able to use in a proposed road upgrade at the A82. The organic fraction that's going to be mixed with the material in the lower cell, which, as you can see here, it's more of a kind of silty loam, sandy loam that really is ideal as a as a way to kind of restore the agricultural land that was used for this pilot. So the plan is to really grade that with the organic matter and then return the field to use. We took samples that did meet the BS 3882 specification for topsoil, with the exception of the nutrients, which can readily be added at any time. A second use that we looked at was to use some of the coarser fractions, the gravel and the sand, to make concrete blocks. These would be used for flood protection on the small Laggan burn. We also made some test blocks, which we tested and achieved a strength of about 7.5 megapascals, which is not bad for a concrete of this type made from fresh sediment. So some of the beneficial reuse options, fortuitously, Transport Scotland have proposed upgrading this section of the A82, putting in a new bridge and changing the curve to eliminate a dangerous bend there. So these works will require quite a bit of aggregate to build the embankments and do all the earthworks required for this. And Scottish Canals are currently in discussion with Transport Scotland to retain the sediment on the site for use in this project, which probably would happen in 2022 2023. And we've been able to contribute to the design of that project from the data that we've collected on the hydrology of the Alkaline Laggan burn that passes through the site. Great, so I'll just kind of finish here just to conclude. We demonstrated the viability of suction drainage, dredging and gravel separation for beneficial reuse, and we produced almost 6,000 cubic meters of aggregates that will be available for the A82 road alignment project. The final material in the lower cell is suitable for topsoil and will be used to restore that field to agricultural use. And that's pretty much. If we've time for questions, I'll be happy to take those, or we can save it till the end.
That's great, thanks Keith. We're keeping pretty much to time at the moment, but yeah, any questions for Keith, please use the question box, fire them in just while we change over speakers. So Eve, if you want to make Tobias our next speaker. Tobias, if you want to just accept that, you should have a prompt.
Yeah, should be working in a moment.
There we go. Yeah. Great. And you should be able to share your screen as well. Brilliant.
Let me see. I still have a bit of changing over here in screens. Yeah. Okay, let me see.
That's it. Perfect.
Yeah.
Okay.
Can everybody see my screen now?
Yeah, that's perfect. So our third final speaker for this session is Tobias Roetting. Is that, have I pronounced it correctly?
Yeah,
close enough.
It's Roetting in Germany, but it's close enough.
And he's going to be speaking to us about passive mine water treatment and a Wales-based pilot trial. So Tobias is a geochemist, hydrogeologist and environmental scientist with more than 19 years experience. He's a principal hydrogeologist at Golda, and yes, he'll be speaking about this project. I've seen the paper of some of the lab work, so it's going to be interesting, I think, to see this is new data, new information today. So interesting to hear about the progress with this project. So I'll hand over to you, Tobias.
Yeah, thanks very much. Thank you for this opportunity to present this project in this Contaminated Land Forum, and I hope it's also interesting for the wider community, even though the topic is relatively specialized on acid mine drainage. To start with, I'd like to acknowledge my colleagues who are also working on this, also Gareth Latouche and Ian Hall at Gold Associates, Louis Siddon and Peter Stanley at Natural Resources Wales, who are kindly funding this research project. José Miguel Nieto and Francisco Macias in Huelva in Spain, and Alba Gomez and Julio Castilla in South Africa at the University of Free State. So yeah, thank you for the introduction. I work mainly on mining projects in consultancy, mine water pollution, mine water remediation, prediction of water chemistries at mine sites, and also recently projects on CO2 sequestration using mine wastes, and also reuse of concrete-based demolition material. And as a very quick introduction, acid mine drainage is, as many of you will know, a major source of water pollution worldwide. It arises when sulfide-rich geological materials are extracted and come in contact with water and oxygen. which causes the sulfides to oxidize and to produce sulfuric acids, and the acid then also can leach out a wide range of metals and other contaminants, which often pose a significant problem at abandoned mine sites where nobody's responsible for making sure that discharge water meets any standards. So in Wales, the country has a long history of mining, and more than 1,300 abandoned mines continue to impact over 700 kilometers of river reaches today. So Natural Resources Wales has started a campaign to clean up the most polluting sites in Wales and are trying different methods to remediate pollution at different sites, because every site is different and needs different treatment methods. Some of you may know active and passive mine water treatment systems. Passive treatment systems are systems that, opposed to traditional, for example, high-density sludge active water treatment plants, only use naturally available energy sources and substrates and can operate over prolonged time spans with only infrequent but regular maintenance. Many of these systems are flow-through reactors, where the mine water flows by gravity through different types of substrates, which can be organic or inorganic. And then the substrate reacts with water to eliminate metals and often to reduce acidity. However, many of these systems tend to clog quickly with metal sludges when treating water with high metal concentrations. And the system I'll present today, the dispersed alkaline substrate, was developed during my thesis about 15 years ago to overcome the clogging and passivation problems. And this consists of a fine-grained alkaline reagent, which is mixed with a coarse inert matrix. And this has been tested widely in Spain, and we have now 2 plants operating at full scale at 2 abandoned mines in southwestern Spain. And now we are trialing this at 2 mine sites in Wales. So the first trial site is Cwmreidl mine in mid-Wales near Aberystwyth, which is a lead zinc deposit, which was mined until about half a century ago. And there are several connected mines along this hillside you can see on the photo. And we have 2 main discharges, added 6 slightly higher up on the hill, which has a high flow and low concentrations of metals, and added 9, which is a bit further down, having low flow but high concentrations. And when you look at the parameters, we have a pH of about pH 4 in the water. In the mixed discharge, we have almost 20 milligrams of iron, 200 milligrams of sulfate, 20 milligrams of zinc, and a range of other metals, and we have to treat a flow of up to 9 liters per second on average if we want to treat the water at full scale. The other trial site is Paris Mountain, which is in the north of Wales on the Isle of Anglesey, and this was the largest source of copper in the 18th century, and it's a massive sulfide deposit, which is similar to the mines in Spain where we are operating these systems. It's an open-cast mine, and you can see from the colors, there's a lot of metal leaching going on in the open pit. And we have very high iron concentrations, 650 milligrams per liter, and also significant zinc, aluminium, and copper, manganese. And the pH is quite low, 2.5. And again, the full flow rate on average is 8.5 liters per second. And these 2 mines are amongst the top 5 most polluting mine sites in Wales. So finding a method to remediate these waters would be very beneficial. So to explain the concept of dispersed alkaline substrate, it is similar to many passive treatment systems, as you can see on the top right, that it consists of a downflow reactor. So mine water is fed to the supernatant on the top, then it flows down through the reactive substrate into a drainage layer, and then through a swan neck out into decantation pond to precipitate metals. And in these systems, we want to have a substrate which is, on the one hand, permeable, so what can flow through by gravity, and which is reactive over a long time. Now this is a challenge because to have a high permeability we need a coarse substrate, but to have a high reactivity we need a large reactive surface area, which you normally achieve by having a fine-grained substrate. So what we do is we combine a fine-grained alkaline material which has a high reactive surface and also which enables a larger fraction of the material to dissolve before it's completely coated by metals. And then we mix this fine material with a core supporting matrix, which provides a large pore space where the metals can accumulate without clogging the pores completely. So the first trial was set up last December at Quimradle. Here you can see the site. It's a relatively small area we have available. And we've put in 3 treatment trains. So the first treatment train treats the mixed discharge from adits 6 and 9. First with a reactive tank which contains dispersed alkaline substrate with calcite. And then a second tank which contains barium carbonate. The calcite is aimed to remove mainly iron and aluminium, and the barium carbonate can react with the sulfate in the water and can also precipitate sulfate. And it also increases pH further and then can precipitate metals like zinc and manganese. And then we have a final decantation pond in train 1, which you can see here on the right-hand side of the photo. For treatment train 2, we have again 2 reactive tanks, first calcite, a sedimentation pond, then magnesium oxide, and then another sedimentation pond, which is here in the center part. And the magnesium oxide can increase pH of the water to about pH 10. At this pH, many of the trace metals like zinc, cadmium, manganese are not soluble and are removed. So this is efficient to remove a wide range of metals which you can't remove by calcite dissolution only. And then here on the front, we have another treatment train with just 1 calcite dust tank, which is only treating adit 9 water, so the water which had higher concentrations and lower flow rate. And this is to see if space available isn't sufficient to treat the entire discharge. Then it may be beneficial to just treat adit 9 water, which has about half of the contaminant loading. And with that, at least we could remediate part of the problem on a smaller footprint. So here we're trying to see how the calcite substrate deals with the higher metal concentration in adit 9 water. And then we could add another tank at the outflow, which could be magnesium oxide or barium carbonate, but for site constraints, we didn't have enough space. So I'd like to present some results from the first 9 months of operation. So first we can see the evolution of pH. In the first treatment train, water comes in at pH 3.5, and in the first calcite tank, it increases to about pH 7. And then in the barium carbonate tank, it increases further. And at the outflow, we have a pH of about between 7 and 8. So near neutral water, which is good for discharge. In the second treatment train, again, inflows at pH 3.5. The first calcite tank increases pH to between 6 and 8, and magnesium oxide increases pH to between 10, 10.5, and then the outflow at the decantation pond goes down to average of pH 9.5, which is a bit high, but it has good treatment efficiency, as you'll see on the next slides. And in treatment train 3, pH is lower, just pH 3, and increases to pH 6 to 7 at the outflow. Now we come to the more interesting part, which are the metals. So iron inflow in the mixed discharge is usually around 20 milligrams per liter, sometimes a bit higher if there's a lot of suspended iron. And the calcite tank is able to remove most of the iron from the water, and then not much happens in the second tank. Same for treatment train 2, and in treatment train 3, where we have iron concentration around 100 milligrams per liter. On average, a single calcite tank can remove about 60 milligrams of iron. So in order to remove all the iron, we would have to add another calcite tank on a treatment train for that water. For aluminium, again, the calcite tank removes all the aluminium from the water, and no aluminium is left in the second treatment tank to be removed. And for zinc, in the first treatment train, we have good removal of zinc in the calcite tank, which is surprising because calcite normally doesn't remove the zinc. But due to the wood chips, we also have some sulfate reduction going on in the tank, and that removes our zinc in the first treatment train. In the second treatment train, where we use a different type of wood chip, which isn't leaching organic carbon as much as in train 2, we have less zinc removal in the calcite tank, but then the magnesium oxide tank removes all our zinc. And in treatment train 3, as it's only calcite, we have hardly any zinc removal as we would expect. So we could add another tank afterwards, for example, magnesium oxide, to remove the zinc in the second treatment step. And for sulfate, in the first treatment train, we get sulfate removal due to the sulfate reduction, which is happening in the tank. In the second train, we don't have sulfate reduction, so we have no removal, as we would expect. And again, in the third treatment train, we don't have any removal. And in train 1, we have some removal in the calcite tank due to sulfate reduction, and then the rest of sulfate is removed by reaction with the barium in the barium carbonate. So overall, we get very good discharge quality for the quimridal water, where we can basically remove all the relevant metals if we treat discharge 6 and 9 together. For Paris Mountain, we set up the system in late spring, and we were starting up the system, filling all the tanks. As we have higher metal concentrations, we need more reactors, and we've installed 2 treatment trains in the trial. The first train has 2 calcite tanks with sedimentation ponds in between, and a final magnesium oxide tank. And the second treatment train again has 2 calcite tanks and then a barium carbonate tank and sedimentation ponds. And here we are using also a initial pre-oxidation tank, which is just a decantation pond, because with these high metal concentration, often some iron will precipitate spontaneously if residence time is long enough and if it has access to oxygen. So we can remove some iron here without any reagent dosing, and then we can start removing more iron in the actual treatment tanks. And at Paris Mountain, we don't have sufficient head available, so we need to feed the system by a solar-powered peristaltic pump, which takes water from the mine adit and then feeds it into the system. We've only just filled the system, so here we can see the first results, which are just pH and conductivity from last week's monitoring. And we can see that pH at the inflow is 2.5. In the first calcite tank, it increases to pH 5.5. Then in the second calcite tank to pH 6.5. And then the magnesium oxide increased pH to 10, and then the outflow we have pH 9.5. So from that pH, we're still waiting for the analysis results, but we can anticipate that most of the metals should be removed in the system at this pH value. And electrical conductivity is relatively constant, around 3,000, 3,500 microsiemens. This indicates that no significant sulfate removal occurs in the system. For the second treatment train, which has the barium carbonate at the end, again, we have a similar increase of pH in the 2 calcite tanks, and then an increase to pH 8 in the barium carbonate tank, and pH 8 at the outflow. which again is a beneficial pH for discharge because that normally meets discharge criteria. Regarding electrical conductivity, here you can see that we have a significant drop in electrical conductivity in the barium carbonate tank, and that indicates that here we probably have significant sulfate removal due to precipitation of barite. And this will be confirmed once we get the analytical results in. So to conclude, the dust system has been tested previously successfully in 2 full-scale treatment plants in Spain. We have preliminary results from the 2 pilot sites and wells which show promising results, indicating that it will also work successfully under Welsh conditions. And if that is confirmed, then it may provide a cost-effective treatment option at remote sites where other treatment systems cannot be applied, either to excessive treatment costs or due to excessive land requirements. And dispersed alkaline substrate could also be used at abandoned mine sites in Scotland, where I think conditions are quite similar to those in Wales. And I'd like to thank you very much for your attention.
Thank you, Tobias, for that. Eve, if you just wanted to make me presenter again, that'd be grand. And bring back on our other speakers from this session. Okay. Right, so we've got a good number of questions. Obviously, people, if you have questions for Tobias as well, please file them into the question box. But we'll start back with Alison. Alison, there's a few questions for you. Have any commercial entities used the observatory so far, and if so, what for specifically?
So we haven't had a huge amount of commercial use of the observatory so far, but we're hoping that that will happen soon. I think we have had interest from people involved in water treatment or clogging of systems, of geothermal systems, also geophysical monitoring equipment, using the compounds, the research compounds, to test out equipment and sensors. So those are the kinds of inquiries we've had, but we're very open to hear any ideas and discuss ideas with people who are interested in doing development and innovation.
Okay, great. And any specific issues in relation to licensing, permitting for either drilling or extraction in terms of liaising with the coal authority?
So clearly there was a lot of permitting and licensing that had to go on. We had to get planning permission, and we have heat access agreement with the coal authority and a supplementary agreement, as well as some permits to drill through coal. So there was paperwork involved, and we also had to work with SEPA in terms of abstraction and discharge permitting, and subsequently permitting for geothermal operations. So actually we were able to use one of SEPA's GBR, general binding rules, for those operations. So there was a lot of that. And certainly for the planning application, there was a lot of work went into the environmental aspects of that application. We didn't have to do an environmental impact assessment, but we did collect a lot of data around that. So I think we had the benefit, being a research project, of being able to look widely. It was really important for us to look widely at the baseline. But there was quite a lot. I wouldn't say there was any particular issues. We just had to work through them all, but it was a time-consuming process. It did take quite a long time.
Okay, thank you. And just one question in terms of the this approach to renewable energy? Where does Scotland sit? Are there other countries that are looking at this technology? Where do we sit at the moment on this?
Yeah, so I mean, there are kind of, in mine water, shallow geothermal particularly, there are some kind of like flagship schemes. For example, there's one in the Netherlands at Heerlen, which is an integrated heating, sort of storage and cooling scheme, where they have a range of factories and buildings connected up to a district heating network, and they both use the heat and store the heat. There are schemes across other parts of the world as well, but it's not particularly well used. There's a lot of schemes going in the northeast of England that the Coal Authority and councils and other people are involved in currently. So in terms of the UK picture, the northeast of England, there's a lot happening there at the moment. It's a very active field. So yeah, and more generally in shallow geothermal, clearly there are plenty of opportunities for shallow low temperature heat in Scotland, and the Scottish government has very much supported pilot studies and feasibility studies for that, and is something that they're keen to work with people on, I think, going forwards.
Okay, interesting. Keith, if we move on to you, I've got a question here from one of the audience regarding sediment separation. So what are the costs of recovery versus costs of virgin aggregate? And a question tagged onto that, was there a cost as well as a financial gain?
Yeah, that's a great question. For any aggregates, a large portion of the cost is transportation. So it's really going to depend on, you know, for this particular site, if you think about the road realignment, you know, what is the closest source of material that could be supplied to the site? The main savings, at least for Scottish canals, were the fact that the sediment was transported through the pipeline, which probably saved about, you know, maybe 400 lorry trips from the point where the canal sediment would have to be unloaded. So that's really quite a big savings over the cost of a traditional dredging operation.
Okay. And I think this is a question: concrete additives available to improve strength in terms of fines. So I don't know if you have any comments on that one there in terms of use of additives.
Yes, and another part of the SURICATES project, we're doing some pilot studies to, you know, take canal sediment, you know, from an urban canal in Glasgow and turn it into a concrete using cement and some different pozzolanic type additives for that. The main barrier to that approach seems to be the carbon content, which reduces the strength of the concrete. Also, from an economic point of view, you've really got to dredge and then place the sediment in its final location. If you have to kind of stage it and wait a period of time before using it, it doesn't really work that way. You've got to be able to kind of use it directly to make it economical, and that's the challenge. But it's what we're kind of working on through the SURICATES program.
Interesting. I'll come over to you, Tobias. We've got a few questions again coming through from the audience. So any thoughts on the longevity of the DAS reaction tanks and the management of metal-rich precipitates produced? Another question that goes with that: problems common to many passive systems.
So the longevity in Spain, we're aiming for a lifespan of about 5 years before you have to replace the substrate. And in terms of reuse, right now we are using wood chips mixed with calcite or magnesium oxide or barium carbonate, which on the one hand is sustainable in that it's often a waste material that you can get hands-on easily, but it may make waste classification more difficult. So it's something we're working on. There's an option if you calcine the material, if you burn it in a controlled facility, then you can concentrate your metals to a very small volume, and then dispose of them. Otherwise, you have to dispose of a metal-rich organic substrate, which can be more challenging. We're also working on testing other materials as our carrier or as our course material, which may be easier to recycle or to separate the metals from the course material.
And a question related to the rise in pH at the Paris mounting test system. So as this is being commissioned, is this due to high surface area initial reactivity, fine particulate reactivity, and will this be suspended? Was the media washed before commissioning to overcome this? Also, what is the mechanism for ion removal? Quite a lot in there, so ask me if you want me to repeat anything.
Sorry, I only partly understood the question. The audio is a bit bad.
So this is just being commissioned. Is this due to high surface area initial reactivity, fine particulate reactivity, and will this be suspended? Was the media washed before commissioning to overcome this?
I'm still not quite sure I get the question. We didn't wash the media. When we mix the dispersed alkaline substrate, we mix wood chips and some water and our reagent powder, so that the reagent sticks on the wood chips and coats the wood chips, and then you can fill the tanks. In terms of pH increase, the pH increases first due to calcite dissolution, and as pH increases, ferrous iron oxidizes more rapidly, and then it oxidizes to ferric iron, and that precipitates as iron hydroxides. And then the magnesium oxide or the barren carbonate increases pH further, and then other metals precipitate. I'm not sure if there was a part in the question about fine-grained material being washed out. The finer grains will dissolve first, but then we have a range of grain sizes, for example, in the calcite sand, and then these will dissolve to finer grain size. So over time, we keep up with the reactivity because some of the reagent is consumed, and other parts of the reagent are still available for dissolution. I'm not sure if that answers some of the question.
I think so. Yeah, no, that's grand. Are there any more questions? Anyone in the back team has any more questions? I'm not seeing anything more.
Tom, I had a question for Alison, if I may.
Yeah, go ahead.
Yeah, Alison, I wonder if anyone had done any investigations in using some of the abandoned coal heaps as a source for local heating schemes, you know, which, as you probably know, do get quite warm. In fact, some of them even catch fire due to the oxidation of the coal dust in these these piles. Oh, can't hear you.
Yeah, I'm not sure there has been a great deal of thought being put into that, Keith. So that's maybe something to note down and to think about for the future.
Okay, if there's no more questions, then thank you very much to the speakers in this session. Thanks to the rest of the team and to our attendees as well for coming and asking some interesting questions as well. So what we'll do is we'll launch the sponsor videos. So please stick around for 10 more minutes to watch those, and then obviously we'll close off the webinar and be back at, I forget what time, 3 o'clock, I think.
3:30, Tom.
3:30, thanks Alison, 3:30 for our session 4, land contamination risk assessment and sustainability. So yeah, thanks everyone, and enjoy the videos now.
Yeah, thanks Tom for hosting that
ERS
session.
is a specialist contaminated land contractor with over 25 years experience of remediation, site investigation and many other brownfield services. We are an independent, fully employee-owned company. Our multidisciplinary staff members are all committed to ensuring client satisfaction. We offer a wide range of investigation and remediation services under one roof, including soil and groundwater remediation, materials and waste management, site investigation, invasive weeds treatment, and laboratory treatability testing. We provide a range of remediation services including chemical remediation, bioremediation, stabilisation and solidification, and process-based remediation. We can prepare comprehensive materials management plans in accordance with clear code of practice, including cost-effective solutions for the disposal or reuse of soils. We offer a full range of site investigation services including high-resolution site characterisation, detailed hydrogeological characterisation, and groundwater and ground gas monitoring and sampling. We can treat a wide range of invasive weeds including Japanese knotweed, giant hogweed, Himalayan balsam, buddleia, rhododendron and many more. Our services are supported by an in-house treatability laboratory. We can assess soil and water and optimise remediation using respirometry and qPCR. Give us a call or visit our website to learn more about our services.
Developing on brownfield land. The demand for development opportunities has led to more competition for brownfield plots. However, these plots can present challenges, particularly in densely populated post-industrial land in the UK. Ground contamination on these sites puts standard construction materials at risk, as their durability tends to be tested in favourable ground conditions. As our understanding of material science increases, so does our understanding of the long-term effects on human health when exposed to carcinogenic contaminants, increasing the importance to future-proof developments to protect workers and residents. Unlock your brownfield potential with Juta UK's GP Titan Tech membranes. These multi-layer thermoplastic membranes prevent the migration of harmful substances and gases into habitable areas, creating a safe environment. For more information, contact Juta UK at www.juta.co.uk.